We're finally on to oxidative phosphorylation. Now, for a long time, the exact mechanism of this was unknown. They knew in the electron transport chain that there were a lot of different reactions taking place with those with NADH, but they didn't really know what was happening. For a long time, what the most popular methods were was that there was some sort of other high energy intermediate, such as those found in the substrate level phosphorylation found in glycolysis, that was driving the ATP synthesis of mitochondria. But they simply never found those intermediates. So Mitchell put forward a theory instead, which is the Chemiosmotic Hypothesis, that there was a proton gradient across the inner membrane that could be used to drive ATP synthesis. There's a lot of good evidence for this. Things like the fact that that inner membrane is impervious to protons and other small charged things like chloride ions or sodium or potassium. Also, if you don't have that gradient set up, or if there's any leaks in that inner membrane, you don't get ATP synthesis. So the fact that you have this proton gradient closely tied to ATP synthesis has been shown over and over again. That chemiosmotic hypothesis eventually won Mitchell the Nobel Prize. Looking at this proton gradient, again, the electron transport chain, which are shown here in those complex 1, complex 2, complex 3, and complex 4, all drive protons across the inner membrane of the mitochondria. It's going to take protons from the matrix to the intermembrane space. In doing so, the matrix then is left without very many protons and therefore a high pH, and the intermembrane space therefore has a lot of protons and a low pH. Those protons will then be able to go back into the matrix through the ATP synthase, which is that which you see on the far left. Getting into the thermodynamics. So this is an equation to describe the thermodynamics of our ATP synthesis, of that chemiosmotic coupling. Delta G here is going to be determined by two main things. One of those is going to be the concentration of protons on either side of the membrane. So that C1 and C2, that relationship is going to be one of the driving forces. The other term then includes this delta for the potential difference across the membrane. So not only does the concentration matter, but also the potential difference, that electrical potential difference, is also going to play a major factor, which is why you also see that cursive F for Faraday's constant, as well as Z for the charge of the proton. While the stoichiometry for how many protons per electron is uncertain, it's generally accepted to be about 6 for succinate and 10 for NADH. So what we have is we're going to have protons being pumped from, again, the inner matrix to that inner membrane space. This free energy is going to be associated with the movement of protons up the gradient. So remember that inner membrane space has a lot of protons, and we're going to pump even more into it. This is not going to be favorable overall. So this pumping is going to have the concentration gradient as well as the electrical potential to overcome. Now, as you look at these equations, notice that we've got 3 different equations here, and they all look different. But what I'm going to be showing you is that they're actually all the same. One thing I want you to notice as we look at these equations is the fact that we have the 2 below. One of them has a positive sign and one of them has a negative sign. The other thing I want you to notice is that not only is there that sign change, but also which of the pH in and pH out are also flipped. So those 2 bottom equations are actually identical. The only difference is that which pH goes first is changed. When those flip, that also flips the sign. As we proceed forward, you're going to see the larger of those 2 equations in black, the one that we use the most commonly. So that is going to have a negative sign in it, but that just comes from the in and out being in the position that they are. So the first thing we're going to do is actually take away the natural log. So as we do that, that's going to give us a regular log, but in order to go from a natural log, which is in the base e, to a log base 10, we're going to need to add a constant to this. Now, I'm also going to be using the negative sign on here, but as explained previously, that negative sign is just for how we're defining in and out. So in this case, I have the proton concentration of out being on top and in being on the bottom. If I were to flip those two things and put in on the top and out on the bottom, we would get rid of the negative sign. I know that's confusing. I'm just trying to be consistent with other instructors. But we haven't gotten rid of the log yet. So we're going to get, so the first thing we've actually done is put the hydrogens in for the concentrations so that we know which one is which. Then we're going to go ahead and get rid of the logs. There we go. So now we have logs of our concentrations, and there's a now constant factor added, that 2.303. In other courses you may have taken, you've likely seen this switch before, where you have a natural log in some equations and a log with a multiplication factor of this 2.303 instead. Then from here, there's something that you might notice. Log of a proton concentration is something we can work with. But right now we've got logs with one proton concentration over the other. It's a little bit messy. So we're going to use a log rule to separate out so we don't have these two proton concentrations one on top of the other. But instead we use a log rule to have one be subtracted by the other. So now that we have log of one proton concentration minus log of the other proton concentration. Now what we're going to do is log of a proton concentration. We've seen that before. That's pH. So now we're actually to something that almost looks like the equation seen on the previous slide, but we still have this Z factor in there. We're going to go ahead and get rid of the Z factor. Everything that we're doing is protons. Protons are just +1. If you multiply anything by a +1, it's just itself. So that Z factor doesn't really play a part in this equation. And so here finally we're back to the beginning, where we do have R is the gas constant, T is the temperature in Kelvin, pH out minus pH in. All of that's multiplied by that negative 2.303 plus Faraday's constant and that electrical potential. So there we finally are. So just note that those two equations really are demonstrating the same idea, even though they look drastically different. So if we're actually going to use these with typical values, that membrane potential is usually positive, that positive 0.8 volts. Then when we take into account pH out minus pH in, realize that that inner membrane space is more acidic. So since that out is usually going to have a lower pH than the pH inside of the mitochondrial matrix, you're usually going to get a negative number for that. Then again, temperature needs to be in Kelvin. So here then we have all of our factors put into place so that we can actually do some more mathematics. In previous videos, we've used Faraday's constant. So that F then here has been replaced by that 96.49 or 96.5 for Faraday's constant. And the temperature then is done in Kelvin to give us finally a positive 23.3 kilojoules. So remember here that when we're talking about this thermodynamics, this is the thermodynamics required to pump another proton across the membrane into the inner membrane space. So this is actually looking at the positive delta G required for the electron transport chain to actually pump protons across. Now realize that when we actually get to use this energy, the protons are now going to fall down the concentration gradient. So the nice thing is now when we're talking about creating ATP, we're going to have a negative delta G to work with. So the process overall then for allowing those protons to rush back in the direction they'd like to go is going to be about negative 23.3 kilojoules. But how are they going to rush back? That's going to be not just all in one go, but we're going to use that negative delta G value. We're going to use that exergonic energy to actually harness it and drive the ATP synthesis using this massive ATP synthase, which we'll be talking about soon.